this talk is almost certainly mistitled because I'm going to spend very little talking about the physics of noise and more talking about noise and physics. The physics of noise is actually really interesting, but it's probably not what any of you are studying, unless you're, well, it doesn't sound like that's what you're studying. And some random musings about experimental errors and ways to check for systematics. This talk is going to kind of bounce around a bit, and I'll apologize for that up front. And if something either is interesting or confusing to you, just stop me. I'm much happier to follow your questions. And if we don't get through all of what I have, that's OK. You'll get that in the handouts. So what is noise? I like sort of to view it as being the gardener's definition of what is a weed. It's whatever you don't want. So here's a pretty clover blossom, but in the middle of your lawn, it's noise. So why do you need to care about noise and errors in your measurements? There's sort of 2 points to it. One is you'd like to make correct measurements. You'd like to know that you're actually measuring what you think you're measuring and that you know how well you've measured it. But also, you want to be able to communicate those results successfully. And I highlighted this because it's something that no one told me in graduate school. And it's obvious, but it's something you just all need to come to terms with. You are going to be living in a low signal to noise world your entire professional lives. And that's what it means to do research. The easy things to measure have already been measured. You're always going to be pushing this low signal to noise edge. And that means you really need to understand noise. There. So why should you care? OK, so when you're designing an experiment, it's really, ideally, you'll understand quantitatively the sources of noise you expect to have in the measurement before you start making the measurement. And I'm going to, if I get there towards the end, I'm going to talk about a really beautiful example of this, where you work through what the magnitude of the different errors are going to be before you start into an experiment, so you know what to expect. As you're going along, keep checking that things are making sense. If you've got more noise than you think you should be having, then you've got some work to find out where the noise is coming from, track it down, try to fix it. But this one is a problem too. If you have less noise than you know you should be having, you need to stop and figure out what's broken. The universe never gives you this gift. A 1K resistor always has 4 nanovolts per root hertz of Johnson noise. If you see less, then you're not actually looking at your resistor. So this one is probably at least as important, maybe more important than the first one. If you've got less noise than you know you expect, then something's broken. And then the final thing, you're in the best position to be the most skeptical of the results that you're getting and the measurements you're making. You know your experiment better than anyone else. You need to be the one who is challenging your own results. And this is really hard, especially when you're trying to finish your dissertation and you just want to get that result, to keep asking yourself, is this right? Have you done the right measurement? Is there something else that could have gone wrong? OK, so I'm not going to get very caught up on semantics, but a few terms, and these are none of these are technical or formal definitions, but it's the natural language that I've seen mostly used in physics. So noise usually means random noise. It sometimes means everything that's not your signal, but it often means random noise, which can be fundamental noise like Johnson noise or shot noise, or added noise like amplifier noise. Shot noise is a specific type of noise that comes from counting fluctuations, either from a finite number of photons or a finite number of electrons. Interference means you're getting someone else's signal getting into your measurement. And that interference could be from 60 hertz line cord, it could be radio stations, it could be pump motors. It's also called pickup. So oscillations is not, it's neither noise in the sense of being random noise, nor interference coming from somewhere else. It's when your own electronics are misbehaving. Usually this comes from an op amp that's decided to start oscillating. this can look a lot like interference, except that it comes from your own electronics. Then drift is particular flavors of noise which correspond to low frequency wanders. It's often lumped together with 1/f noise. It's often due to temperature sensitivities. Okay, so usually I'm going to be talking about noise as having a zero average. So it's something additive to whatever else is going on with your signal. The usual statistic, and this is just some noise I've captured on my scope. The way you measure noise, and this is a random noise, not pickup, is in the power of the noise, or the voltage squared. But it's hard to think in terms of volts squared, so you'll almost always see noise measured in volts RMS, or you'll see nanovolts per root hertz. I'm going to show you on the next slide. But the real quantity is volts squared, or power. Noises, because they're incoherent, they add together as powers. And you probably all know RMS, it's the square root of the mean of the square of the signal. So noise power is always going to be an RMS. When you need to add noises together, you're adding the powers. If you have a few amplifiers that are coming together, the easy way to think about the noise is go back to volts squared or volts squared per hertz, add those together, and then you can figure out how much RMS noise you'll have at the end. So this is an example of a really nice op amp, by the way. It's a differential output op amp that TI came out with 5 or 6 years ago. The THS 4131. It's fairly quiet. The broadband noise is just about 1.5 nanovolts per hertz. And it has a 1/f knee at a few hundred hertz. You'll see plots like this all the time if you look at electronic data sheets, where they'll plot noise in terms of this unit, nanovolts per root hertz, per square root hertz. And again, that's that you can see the noise linearly in voltage. The real quantity is the power spectral density, which is volts squared per hertz. And if you want to understand how much RMS noise you would get, say, from this amplifier over some bandwidth, you have to add up the square of this curve, not the curve itself. I'm going to do that right here. So this amplifier's data sheet actually is remarkably well described with just flat noise plus a pure 1/f term. The blue curve I've overlaid here is just this function with a flat noise term at just under 1.5 nanovolts per square root hertz and a knee at 325 hertz. And so if you wanted to understand, say, the question is, what's the RMS noise that you'd get from this amplifier in a bandwidth from 1 hertz to 10 kilohertz, you'd integrate, there's supposed to be a 10 kilohertz up here, I'm sorry. You'd integrate this power spectral density over that band and then take the square root of it. And that integral is actually pretty easy. The first term is just going to be a constant, so you'll just get the bandwidth. So it's going to be 10 kilohertz minus 1 hertz. The second term is the integral of 1/f, so that's just a logarithm. And I have another unfortunate line break. But so that's the knee frequency times the natural log of the ratio of the frequencies. You plug those together and you get the noise times this square root of the bandwidth, which was 10 kilohertz, plus the 1/f contribution, which is just under 3 kilohertz. So in that band, you'd get 165 nanovolts per root hertz. And you'd be able to see this better if the line didn't break, but I wanted to point out specifically how the 1/f noise only adds a constant amount of noise power per decade. And when I talk about 1/f noise in a few slides, I'm going to come back to that. But this factor actually is always just, so this is a good rule of thumb to have. For each decade of 1/f, the natural log gives you a factor of 2.3. This is just natural log of 10. So 2.3 times wherever that knee frequency is, that's the 1/f contribution to the broadband noise of some system. So here, our knee is right around here at about 300 hertz. Every decade is going to give you the equivalent of about 700 or 800 hertz of noise bandwidth. And I took a bunch of decades here going down to 1 hertz. But if you took this curve out, say, to a megahertz or 10 megahertz, the 1 over f contribution probably doesn't matter anymore. Okay. Oh, well, that didn't print well, but actually I can tell you what's important here. Power spectral density is a good way to describe noise formally if it's a stationary process, which means that the properties of the noise are not changing over time. There's another term that gets used here, which is ergodic, and that means that the statistical average or the ensemble average of the noise properties is the same as the time average. For almost everything that you're looking at, these are going to be true practically. Whereas formally, they'll never be true because the time average of everything in a mathematical sense is 0 because you always have to integrate over all time, and your experiments have a finite duration. But in a practical sense, your noise is probably going to be ergodic and stationary. And there's a fact here which didn't get cut off, which is that the autocorrelation function of your noise is the Fourier transform of the power spectral density, and vice versa. And that's useful for a trick. And I just wanted to mention this trick. That's the whole point of this slide. The fact that you can measure the power spectral density of a noise source by measuring its autocorrelation allows you to get around the limitations of amplifier noise. And this trick really works. So if you have some system, say it's a JFET preamplifier that you've worked really hard on, and you think it's only a nanovolt per root hertz, but you'd like to characterize that, and you have an analyzer here that has 5 nanovolts per root hertz of input noise, and you don't want to have a lot of extra gain. You want to just try to measure this very low signal. You can use, this is an FFT spectrum analyzer. You could use 2 separate input channels and measure the cross correlation of your system. So take your noise source and plug it into both channel 1 and channel 2, and have this spectrum analyzer measure the cross correlation of what turns out to be the same signal. And then you take the Fourier transform of that. That is the power spectrum of your signal, where with averaging you remove the effect of the noise of this instrument. And I've done it to use this actual instrument to measure the Johnson noise on a 50 ohm resistor. And so the technique actually works. Okay, so now I'm going to talk a little bit about noise sources. The first one I've already talked about a little bit is Johnson noise. Every resistor has Johnson noise. It doesn't matter how well you make a resistor. If it has resistance, it has to have Johnson noise. This is a fundamental physical property of resistance. Johnson noise scales like the square root of temperature. The Johnson noise power is linear in temperature and linear in resistance. So in nanovolts per square root of hertz, it goes like the square root. A couple of rules of thumb for room temperature resistors. A kilo ohm is about 4 nanovolts per root hertz, and 50 ohms is about 1 nanovolt per root hertz. And this spectrum is extremely flat up to most of the frequencies that you'll ever look at electronically, at least at room temperature. It's true up to a few terahertz. So electrically, if you need to model how Johnson noise will come into your experiment, either of these 2 models is equivalent. You could either view a noiseless resistor in series with a perfect 0 impedance voltage source that has the Johnson noise voltage, or an infinite impedance current source with the Johnson noise current, which is just the voltage noise divided by resistance. A surprising thing I discovered, maybe it's not surprising, it was surprising to me, or not obvious at least, the first time I was working on transimpedance amplifiers. So this is a simple amplifier where you convert current to voltage using a resistor in the feedback. The current noise referred to input of this amplifier goes down with larger resistors, not up. So bigger resistors have lower current noise equivalent, even though they have bigger voltage noise equivalent. The way to understand that, there's a bunch of ways to understand it. The way I understand it is this resistor will always have Johnson noise, and so his voltage Johnson noise will go up like the square root of resistance and that shows up as a voltage noise on the output. But the current increases linearly with R, or the gain, I should say, increases linearly with R. So if you refer that output noise back to the input current, you divide it by R, the noise is going up like the square root of R. So the input referred noise scales like 1 over R. So that's, if you're measuring current and you have to make custom amplifiers, bigger resistors up front give you the best noise performance. There. So I want to come back to that paper I mentioned earlier from Bob Dickey. It's about 8 pages long, and it's kind of a cultural pillar of physics, and I recommend you all read it. It's very accessible. It's falsely considered to be the invention of the lock-in amplifier, but it does have some other really nice elements in it. Besides inventing the Dickey radiometer, it opens with about a 1-page discussion explaining how Johnson noise is really the same thing as blackbody radiation. And I want to just walk through verbally how that works, because it's just very cute. So Dickey begins by imagining you have some antenna inside of a cavity with black walls. The antenna has some characteristic impedance, and it's coupled to a transmission line with the same impedance that's terminated then with a matching resistor. All of this is at a constant bath temperature T. And then he says, well, so imagine what happens with blackbody radiation that will come and impinge on the antenna. Some of that will be coupled into the antenna and then go down this transmission line, and because the resistor is the same impedance, all of that power will be delivered into the resistor. At the same time, the resistor has some Johnson noise, and so that voltage noise is also coupled well to the antenna through the transmission line and radiates back out to here. If those two processes aren't in balance, then energy will flow either into or out of that resistor, violating the second law of thermodynamics. And the blackbody radiation in here scales like frequency squared. The Johnson noise is flat, and that factor of nu squared just comes from the antenna efficiency, the lobe pattern that you get from a dipole. That also explains where the high frequency end is to Johnson noise. It's the same as the Wien limit in blackbody radiation. So when HF approaches KT, it no longer looks like a flat spectrum here, or this F squared in blackbody. Anyway, so that's actually, there's nothing practical about that. It's just a cute result that I couldn't resist walking you through. Okay, so shot noise, I'm going to just mention briefly, is due to the fact that current flows in chunks, typically electrons, not as a smooth fluid. And so in any interval delta t, there will be a finite number of electrons based on the magnitude of the current. From Poisson statistics, the variation on some counting process n just scales like the square root of n. So the variation or the variance, the RMS on the number of electrons in some interval of time flowing in a current process is here. It's just the current divided by the charge on an electron times the time interval. To convert that to a noise current, you'll just multiply by this number of charge carriers corresponds to this number of amperes of noise. If you call I0 the average current that's flowing, then the RMS current is going to be here in that interval of time. Convert that to a bandwidth by dividing by delta t. You finally get this equation for the RMS current noise or shot noise. To convert this to a power spectral density, we just square it, and the delta F comes over here. So the current noise per hertz is just 2 times the charge on an electron and your current. This shot noise appears on things like photodiodes or conduction through on counting statistics on a photomultiplier tube. It doesn't apply to conduction of currents through metals because of long-range correlations. And there. So 1 over F noise. And it's always written like this, and it's almost always pronounced 1 over F. It's also called pink noise or flicker noise. It corresponds to power spectral densities that scale approximately like 1 over f, or f to the minus 1. The power law can change, but it generally looks like this. Many systems exhibit 1 over f noise. This is the cutest plot I was able to find from an old talk that was given by John Clark in 1976, describing 1 over f noise level in the flood levels of the Nile River. And it's data that spans over 1,000 years, and it shows 1 over f continuing all the way down to a 10 to the minus 11 hertz level. This is one of the reasons that lock-in amplifiers are so handy, is 1 over f is really universal. There is, I would say, a mostly philosophical question or argument as to whether 1 over f noise really goes on to 0 frequency. I say it's philosophical because there is no 0 frequency. The universe has a finite age. It's only 12 billion years old. And remember, you get, especially if it's really 1 over f, you only get a finite amount of noise power for each decade. And so if you're going from 1 hertz out to the age of the universe, that's only 18 or 20 decades of frequency. It's just not that much bandwidth for 1 over f power. Some other examples of real 1 over f. This is from this low-level noise handbook. Actually, this is a really good reference. Keithley has been publishing this book at least for 30 years. It used to be in a little red book. I think it may only be in PDF format now. But if you don't have a copy, I think you can just download the PDF if you Google that. It's just a very good reference. This is an example of excess noise in resistors measured from a tech note that LIGO published a few years ago. In addition to having Johnson noise, resistors can show excess noise that's often proportional to current. There's a lot of controversy over where that noise comes from, whether it's temperature fluctuations within the resistor, resistance fluctuations. But better resistors have less of it. Worse resistors have more of it. If you're building an experiment that requires the most stable resistors with the lowest excess noise possible, there's a series of resistors built by Vichy using something called bulk metal foil. They're very expensive. They're $10 resistors for one resistor, but they're as close to an ideal resistor as I know of. Okay, amplifier noise. I'm going to use the SR560 as an example and just go through a little bit how to figure out or understand what the noise properties of an amplifier might be in your experiment. And this is just like with the op amps, this is the power spectral density, the square root of power spectral density for the input noise with the input short-circuited on a SR560. It gives you a pretty good idea. It's pretty quiet out near kilohertz and above. It gets quite noisy when you get down to 1 hertz. Not so bad at 10 hertz and 100 hertz. But you could do a lot better at understanding how and where to use an amplifier with a little more information. And so I'm going to spend some time discussing something called the noise figure. It's sort of a nuisance to generate these, and so I have to apologize. SRS hasn't been perfect at always publishing noise figures for every amplifier we make. We were better at it in the past, and it's something that I keep bugging people to do. But I'm going to walk through now how to understand this plot, because this really gives a more complete explanation of where this amplifier will work for you all in one figure. But it's a little confusing. So first we have to look at what is this quantity noise figure. It has a very specific definition. It's a log scale, so it's a decibel scale. So 20 times the log base 10 of the effective output noise, or the measured output noise of your amplifier, divided by the source noise times the gain, where source noise means Johnson noise. And so that means we have to know something about the source impedance that your signal is coming from. And so here, the vertical axis shows the source resistance in ohms, and you have to also specify this is at room temperature. So this all would change if you had a cold source resistance. But this is so at room temperature. And then frequency from 1 hertz up to a megahertz. And this oval here corresponds to the sweetest operating space for the SR560. If you're operating with a source impedance that's between 100 kilo ohms and a mega ohm, and between something around 100 hertz out to maybe 10 kilohertz, the amplifier is nearly perfect. It adds virtually no additional noise above what your source resistor has in the first place. That Johnson noise here, gained up by the amplifier, is virtually all that you see. The SR560 is only going to add 0.05 dB of additional noise power. That's what noise figure is telling you. So what about down here? Suppose you have a 1 kilo ohm source impedance. Does the SR560 somehow ruin your signal? No, it doesn't. It's perfectly good down here. What you see here, so the SR560 has about 4 or 5 nanovolts per root hertz. A 1 kilo ohm resistor here is also about 4 nanovolts per root hertz. So if you have a source impedance here, this shows you that the SR560 adds about 3 dB of noise power. It adds a comparable amount of noise power to what the source impedance, your Johnson noise, in your signal will do as well. So now if you had a really low source impedance, say 10 ohm source impedance, the SR560 would add a lot of noise. The 4 nanovolts per root noise, 4 nanovolts per root hertz of input noise that the 560 has would dominate the noise, at least based on your source resistance. Now, maybe you have a low source resistance, but there's other elements of your signal that have noise. This won't reflect that. This is just referring to the Johnson noise of your source impedance. There's an easy mistake people can make where I can get a much better noise figure if I just added a big resistor in series with my signal. Right? If I put a mega ohm in series with my little 10 ohm source, my noise figure will drop to 0.05. And yes, you've made a better noise figure, but you've ruined your measurement. That actually doesn't improve the noise properties that you're measuring. It just means that the amplifier isn't the problem anymore. Your 1 mega ohm resistor has become the problem. So in terms of understanding what noise figure means, it's a way to score the amplifier relative to a source impedance. There's other information here, though, and that's where this is why this is better than just a curve showing voltage noise. So this upturn here is due to the 1 over F noise. And you actually get that from the voltage noise curves to start with. This upper part here, though, how come as you get to bigger and bigger resistors, the noise starts to go up again? Well, that's actually due to shot noise on the bias current that leaks out the FETs. So the JFETs are very low bias current devices. The gates will have a few picoamps of input current, but there's shot noise on that gate current. And that shot noise, when you start to get to 10 to the 7 and 10 to the 8 ohms, will start to increase the effective noise of the amplifier. So this is what you're seeing here is due to current noise at the input that's coming from the amplifier going through your source impedance. The corner here where we're losing some signal, this is due to the finite input capacitance of the SR560. And what's happening there is not that the amplifier is getting noisier, but we're actually losing gain. So the input capacitance, together with these large source impedances, is creating a parasitic low-pass filter, and it's filtering out the signal before it ever gets to the amplifier. So that filter ends up being in series with the gain, and you're losing signal. So source figure is a way to understand an amplifier and how it applies to a measurement. Okay, some external noise sources. Oh, yep.
Could you talk a little about a comparison between, say, the 560 noise figures and 554?
554. Oh, yes. Yeah, absolutely. Yes. Yep.
That has a different mechanism.
Yes.
You don't have the amplifier.
No, absolutely. So the SR554 that Scott's referring to is a small external preamplifier. It's actually not so small. It's very heavy. It's a 100-to-1 transformer. It's a very low noise transformer that we have made. There's also an active amplifier you can switch on or off that adds another factor of 5 gain, but it's easy to think of just as the transformer. It has, actually I'd love to put up so if I do this talk again, I will add that as a comparison to this, because it would be really good to compare. The SR554 has a very low or relatively low input impedance, but very, very low Johnson noise. The intrinsic noise of this is just the resistance of the copper wire that makes up the transformer windings. So it's well below a nanovolt per root hertz. However, if your source has more than a few hundred or maybe a kilo ohm of impedance, it can't drive the coil, and you lose gain. And so it would be really awful up here at relatively high source impedances. But if you have a signal that's in this range from certainly from 100 hertz to kilohertz, maybe a few kilohertz, and source impedance that's under 100 ohms, the 554 will do much, much better than a 560. It'll do better at lower frequencies as well, but the gain's not flat. And so you can operate, so one of the things that's nice about running someplace where the gain is flat, not running up here where there's a roll-off of the capacitance, is if your frequency wanders a little bit, you're not also coupling in a variation in your gain. You can get lots of gain out of a 554 at frequencies where the gain isn't flat, but it's sort of a treacherous place to operate because any small variations in frequency will modulate the gain of the response. Yeah? Oh, if you're not in the flat spot. Absolutely. So if you're in the flat part of the transfer function of the amplifier, you're a lot less sensitive to that. But if you're in the slope of where the gain is rolling off, you can get a factor of 20 dB gain, a factor of 10 gain, but you'll be more sensitive to physical variations in the transformer. So external noise sources that get into your experiment, you obviously want to minimize them from the start. Averaging sometimes will help. It may not always help. It depends on what's going on and what sort of noise you have. Some noise sources will interact with your experiment. They could be heating a sample. No amount of averaging is going to change that effect. You just need to remove the source. If there's some pickup at an amplifier that's not coupling back into your experiment, and it's not correlated to your measurement frequencies, you may be able to reduce that by averaging. Okay. So I'm going to talk about a few of the mechanisms that have how signals actually get into your measurement. And a lot of times, especially in the beginning, you can feel that there's voodoo here, and there's really no voodoo. These are very simple coupling processes. And so as soon as people start kind of waving their hand and saying, well, it's getting in there somehow, you should sort of step back and say, well, how is the signal getting into your experiment? There just aren't that many ways. And when you can figure out what's actually happening, you can then make a lot more progress on resolving it. So first I'm going to talk about capacitive pickup. And so just imagine you've got some experiment here, and then some noise source, and everything is capacitively coupled to everything else. It's just a matter of how much. And I have a small worked example here. Imagine you have two little exposed bits of metal, a square centimeter each, separated by 10 centimeters, something like that, like my fingertips. That parallel plate capacitor has about 9 femtofarads of capacitance. Not a whole lot, but if you have 60 hertz, 120 volts driving that, the current that can flow through that capacitor may be 40 picoamps. And 40 picoamps can be negligible or swamp your experiment, depending on where you are. And that's just an example. These estimates are easy to make. You could kind of look at an experiment and get some idea of how big some coupling might be. So what are the ways to mitigate it? There's a few general strategies. Turn off the noise source if you can. Now, if this is coming from the power supply that's driving your experiment, maybe you can't turn it off or you don't have an experiment. But where you can, turn them off. Distance is your friend also. On the lock-in amplifier, I said earlier that we always have the reference oscillator as far away from the preamplifier. Partly that's just to minimize these parasitic couplings. Ideally, you try to design measurements of voltage at a low impedance, so which would then mean that the voltage effect of this current could be smaller. So if you can buffer your detector, then the effect of 40 picoamps just gets swallowed up by the output of your op amp. and may not be a problem. And then finally, shielding can help, specifically grounded shielding. So in the case of this little parallel plate capacitor, if I put a metal plate through the middle of there and ground it, that'll make a dramatic reduction in this 9 femtofarads of coupling. If you don't ground that, if you just put a piece of metal in between, it doesn't really do very much and can actually increase the coupling. Okay, inductive coupling. This is where your transformer and the noise source act as, or your experiment and your noise source act as a transformer. So this is the secondary, there's the primary, and there's some magnetic flux coupling through. And this happens if you have varying currents, big currents. I imagine there's some big currents here. How do you resolve these? So again, if you can turn off a noise source, then that can help. If you have a fan that's keeping you cool, or some pump that's not needed as part of your experiment, and you can turn it off, then just turn it off. Reduce the loop area of potential pickup by using twisted pairs, coaxial cables. Pay attention to how you dress the cables in your experiment so that you minimize the area of this loop that can couple flux. You can try to do magnetic shielding, which would then work to try to divert these flux lines away from your loop. You can use mu metal, use other metal, ferro, like iron sheets. You can try to rely on, if you have high frequency currents, then aluminum or copper can work, where the eddy currents that get induced in those can provide some shielding. And then finally, if your experiment is measuring currents, then try to actually go and measure the current directly and not voltages from high impedance detectors. And so that'll, measuring the currents that are actually being driven from a current source will make it less sensitive to magnetic pickup. Okay, resistive coupling and ground loops. So these will always be part of your life if you're doing any kind of interesting experimental physics. And so you hear about ground loops. It's really very simple. Just imagine you've got some noise source that's going to be injecting its current through the same path to ground that your experiment is using. And so your signal ends up riding on top of some other voltage that's being driven, because this resistance is not zero, and it's never zero. So single point grounding is the universally recommended recipe to avoid this problem, and it absolutely works, and you can almost never really do it. Just think of the connections between your lock-in amplifier and your preamp and all of these BNCs, many of which are going to ground to the chassis, all the different chassis connections that are going on. I think there's an exercise in some of the practice about trying to find the ground loops. So this is a principle, but you'll never actually have it perfectly on any non-trivial experiments. You can also try, where you have to have a common ground return, minimize this resistance. Use really heavy ground buses. This is sort of the brute force approach. You can get some improvement that way. Better still is if you can, this is sort of a part-way path to single point grounding. Remove, if you have one large current source, remove its path back to ground from the one that your detector signals are following. And then ultimately, if you can do differential measurements, and I'm going to talk a little bit about 4-wire measurements as a form of that, then you can make, if you can measure from there to there differentially, you can get a lot of immunity to ground noise. You've now reduced it from being a direct noise source that's adding to your signal to being something called common mode. It's adding to both ends of the differential signal that you're measuring, and you can count on 20, 40, 60 dB of rejection of that artifact if you're measuring differentially. Oh, yeah.
Single point grounding, just to make sure I understand.
Yep.
That means you only have your experiment detector on ground, nothing else.
No, it means that you pick one point, and maybe it's the ground at the power outlet where you're running things to. You have each loop has a separate path back to your grounding point. So maybe you define your single point ground to be the chassis of the dilution refrigerator.
Have a single point ground at every stop. It's marked single point ground.
Excellent.
That is your single point ground. It's a giant top.
So most instruments will have a lug on the rear panel that lets you ground the chassis. But you should realize that that probably also is tied together to the safety ground on the line cord. So if the instrument's plugged in to a wall, that's one path to ground. If you then use a banana cord to try strapping the chassis to your single point ground, you may have just added another ground loop. I hope I didn't give away one of the practicals, but okay, so I talked about differential measurements. These diagrams come from that Keithley handbook. It's worth going over. This worked example is for the case of just measuring resistance with a multimeter. The principle applies to many types of measurement. If you're trying to, here you're going to measure some resistance with a current source, but you're going to have the excitation current flow through the same leads that are also making the measurement, then the lead resistance will add some additional voltage drop. This is related to the issue of ground loops. It's just resistive coupling. It doesn't look like a ground loop here because none of this is ground, but it's the same problem. The solution to this, which you may be familiar with if you've used benchtop multimeters and 4-wire ohm measurements, good ohm meters will allow you to use separate wires to do the current excitation from the voltage measurement. And so this current source, there'll be some lead resistance for the current path going both ways. That'll add voltage burden to the current source, but as long as the current source hasn't saturated, you don't care about that. The voltage across the resistor is being measured by a voltmeter, and the only effect that this lead resistance has is reacting with the input impedance of the voltmeter itself, and that should be very high. Ideally, an ideal voltmeter is infinite impedance. So there should be very, very little current flowing here, and so that's the trick. Okay, oscillations. So this is not a form of pickup. It's not really a form of noise, other than in that sense of the first slide I said, it's not what you want. It's a weed in your garden. This is an example just from an app note from Analog Devices showing a response of an uncompensated or an undercompensated op-amp to a step function. This is the input, this is the output you want to have, and this is the output that you have if you don't have proper loop compensation on this op-amp. The signal is still there, and actually it's got the right gain, but there's this hash on it, which is due to a high-frequency oscillation in your op-amp. You could look at a trace like this and think, oh, I could fix that just by filtering it. If I just have some low-pass filter, I can get rid of that high-frequency stuff and get a good measurement. Don't take that approach. You really need to fix this. Having circuit elements oscillating that you don't want to have oscillating is just trouble. It means, first of all, that amplifier is at a much greater risk of performing or behaving non-linearly. Parts of the amplifier are going to be stressed. The input protection circuit on the op-amp might be rectifying, and say there could be strong non-linearities. It could be overheating. This AC source is now rattling around somewhere in your experiment or your readout chain. It has a much better chance of coupling in through capacitive coupling, which will get worse with high frequency. There's lots of reasons why circuits will oscillate, and that's outside the scope of this talk. I'll just say the most common one that I've encountered is when you hook up a cable to some circuit that you've built. So if you have a little amplifier and an op-amp, and then suddenly, and everything's fine, and then you hook up a 6-foot coax cable, you've added maybe a couple hundred puff or 100 puff of output capacitance, and that often will destabilize a circuit. Put a small resistor in series with the output of the op-amp right where it goes into the cable, and that may solve that problem. That's the only circuit trick I'm going to give you. AC interference can also cause nonlinearities, and I'm guessing because you have high fields here, you probably don't use a lot of diode thermometers. It's probably all resistive thermometers. But so diode thermometers in particular are sensitive to AC pickup in a way that causes DC errors in the thermometry. It doesn't just add noise, because the diodes will add some rectification to that. And so there's a nice plot from the Lakeshore catalog that shows if you have, for instance, a millivolt of RMS noise, that can introduce a 0.1% thermometry error on your diodes. AC coupling also can, of course, cause self-heating of samples. Okay, so drift. This is an example from an app note on one of our laser diode controllers. This is showing the output of some instrument running over 24 hours. And you see the current's not stable, although the scale here is in parts per million. So we have here's the absolute scale. Current's pretty stable until you zoom in, and then you see these variations. There's more power at longer periods of time than at shorter periods of time. This is part of what contributes to 1 over F noise. But if you may notice, well, there's some structure in there. And the structure is TempCo. So this second plot here is showing the room temperature during the time that we took that data. And you could just see by eye a pretty strong correlation between what's going on here and the room temperature. And we actually estimated the TempCo of this instrument from this cool-off cycle here overnight. This will happen in almost any lab you're in. Air conditioners come on, turn off. Depending on how your building is set up, they may turn off over the evenings and weekends. And if you see patterns that seem to be offsets that are drifting with 20-minute kind of time scales, 30-minute time scales, look for something that's going with room temperature.
Or humidity in Florida.
Right, I guess actually, right, I'm used to California where it's always dry. So more drift. So drift isn't always temperature. So this is data from analog devices looking at some band gap references they have. These are voltage references controlled at a constant temperature over 40 days. So drift can also be due to burn-in. That's what they're showing here. And then long-term drift, there's some wander here. But that's not temperature drift because it's being run at a stable temperature. These are some of those exquisite Vichet bulk metal foil resistors being burned in over the course of a year. This is showing the drift rate, so in parts per million per hour. Okay, other sources of noise. And this isn't a complete list by any means, but it's just a few that seem most relevant. So microphonics, this is just when stuff vibrates. And it's usually capacitive. So if you have two wires, there's some capacitive coupling between them. If the wires move, the capacitance changes. And that change in capacitance can induce voltages and currents. This is a picture from the Oxford Instruments publication, Principles of Dilution Refrigerators, where they point out the advantage of having here using copper braids to cool experimental stages while allowing mechanical decoupling from the pulse tube refrigerators that are vibrating up higher. And that's all to minimize the coupling of microphonics into your experimental stage. Triboelectric is another source of noise that I wanted to put these two on the same slide just to point out triboelectric is not microphonic, even though they both come from vibrating things. Triboelectric noise is something that happens in cables due to friction of the insulators moving against the conductors. And it's kind of like when you rub a balloon against your hair and you can just generate some additional static charge. It's that static charge then hopping internally to the cable. And so when you flex some cables, you could get serious amounts of low-level currents popping. There are cables that are made specially to minimize this. Keithley sells them. We now have some with our current source. The key is that you add a layer of a semiconductor, like a graphite or some other conductive layer against the insulation that acts as a conductive lubricant and makes sure that charges can't ever build up on the insulator. And there are cable manufacturers that, like Belden, will make low triboelectric coax cables. it turns out it's very hard to find sources for low triboelectric triax cables. There are some cable manufacturers who make them. We found one in Sweden that we're using for the cables we supply with our current sources now. Okay, the last effect I'm going to talk about is the thermoelectric. So this is when you have junctions of dissimilar metals. Mr. Seebeck, over 100 years ago, figured out that you get an electromotive force from that. They're generally small. In fact, you usually have to work pretty hard to get a big voltage from a thermocouple. That's why people engineer thermocouples. But if you're making measurements at the microvolt level, this will absolutely plague you. It's another reason why lock-ins are so handy. If there's any way to make your microvolt measurements modulated, because this effect won't modulate. This is a DC, it's like a little DC battery in series with your measurement. And this chart from a linear technology app note gives some typical thermal potentials from different junctions. So just a mated BNC junction might have about half or 0.4 microvolts per degree C of thermal EMF being generated. Mated banana jacks can vary between a third and maybe 1 or more microvolts per degree C. There's one thing I wanted to highlight from this chart, and that's the Seebeck coefficient you get from copper oxide. So if you have some bare copper and it starts to oxidize, that can approach a millivolt per degree C. It's really, really awful. This is why contact should never be bare copper. It's one of the reasons why contact should never be bare copper. Okay, I don't have a lot of time left, but I'm going to talk about a few examples of looking for spurious measurements and different techniques that you could use for cross-checking or double-checking your data, trying to understand sources of noise. And the first I'm going to look at this experiment we saw in the lock-in talk, the double modulation experiment. And when I read the paper, one thing that I thought could easily be a problem is this microwave source being turned on and off. Well, so you could imagine pretty easily that could couple into this second lock-in amplifier. Maybe the front end picks up a little bit of the microwaves and rectifies it in band. Maybe the power supply here modulates the temperature of the lock-in. I mean, there's lots of ways that you could have a coupling, and this is a very small signal. There's a part in 10 to the 4 of this signal being measured here. So trying to find other ways to make sure that what you're measuring is what you think you're measuring. One thing I could imagine is keep this running, but put some sort of microwave absorber to block the illumination down to the 2D electron gas. Make sure the signal goes away. Make sure that the detection wasn't spurious due to some coupling in here that had nothing to do with your sample there. Another might be to keep this source running DC and use a chopper wheel with either a reflector or an absorber to introduce a different way to modulate the microwaves into there. No one of those methods is meant to be foolproof. The idea is if there's a way to try to arrange, especially a sensitive measurement, more than one way to see that you're getting a consistent result, that gives you some confidence that even if there was a problem with one or the other way, they probably weren't the same problem, and you now need to invoke a conspiracy of errors aligning to give you that false result. Okay. So this next example I want to give of really understanding your errors comes from the LIGO experiment. Probably, if you watched the news at all, you saw a couple of months ago, LIGO got a detection of a gravitational wave coming from a binary black hole merger. There's a research note that was published by one of the PIs of LIGO, this guy, Ray Weiss from MIT, that was published in 1972 when the ideas were first coming together. And you can find this paper here. You'll have the link later. It's worth taking a look at this paper to see an example, one of the best examples I've found of really working through what the systematic errors and the noise sensitivities of an experiment will be before you ever get started. So this paper went through and identified 9 noise sources that would limit the performance of a laser interferometer for measuring gravity waves. And the biggest one, the one I'm going to look at a little bit, is the shot noise from the laser power. So there's a finite number of photons coming in the laser beam. That limits your ability to measure the fringe on an interferometer. But the paper went through all the way down to looking at the momentum transfer due to cosmic rays hitting the test masses that were carrying the mirrors, and how much RMS jitter that would cause to the mirrors. All of these sources, except maybe for the cosmic ray noise, have been worked on for the last 40 years as part of this experiment. So the shot noise term, there's an expression that they worked out that describes, and this is again a power spectral density of displacement. So this is in meters squared per hertz of positional jitter noise, which is the signal from an interferometer related to the laser wavelength. There's Planck's constant. This epsilon is the efficiency of the photodetector. P is the laser power going into the interferometer. B is the number of passes through the interferometer, so that's an optical gain you get. So how much more does the fringe move than the mirror? And then R is the reflectivity of the mirrors. So the numbers that were in that 1972 paper assumed a half-watt laser with a 500 nanometer wavelength, 0.5% loss on the mirrors, and 50% quantum efficiency and this worked out to be about 2 × 10⁻37 meters squared per hertz as sort of the shot noise limit of what the interferometer could do. All the papers that LIGO publishes now change this from being a positional noise to a strain noise. So strain is delta length divided by length. So the interferometers are 4 kilometers long, so we divide this by 4 kilometers squared to get a strain noise of about 10⁻22 per root hertz. That was what they thought they could do in 1972. Putting in the numbers from the current paper, 43, 44 years later, laser power was 20 watts during the detection. They're using a neodymium YAG laser at 1064 nanometers. The mirrors are better. The quantum efficiency is better. Using the equation from 1972, the shot noise was expected to be about 4 × 10⁻24 per root hertz. And the actual detection that was published in February, this section of the strain noise is photon shot noise limited, and it's about 6 or 7 × 10⁻24. So pretty close to the noise estimate from 40 years earlier. Okay, the last example of checking for systematics. This comes from an old experiment that was flown on a satellite in 1989 to measure anisotropy in the microwave background, called Coby. Published results in 1992. And I'm going to talk about, just very briefly, this experiment, the differential microwave radiometer. It had 6 radiometers that were measuring differences in the sky temperature, separated by 60 degrees apart, 2 identical radiometers at 3 different frequencies, 31.5 gigahertz, 53 gigahertz, and 90 gigahertz. And by the way, this is closely related to that Dickey radiometer that was published in 1946. Okay, so what I wanted to talk about with the Coby result is the idea of dividing your data in half in a way that, if there's a way that you can combine your data that should be sterile of signal, but still have all the systematics and noise properties, like the quadrature output, the Y output of a lock-in amplifier, it's a very compelling way to convince an audience that your result wasn't introduced due to your analysis. So that paper published, these are all sky maps that are generated through a very complicated data reduction procedure. These variations in temperature correspond to tens of microkelvins on a 2.7 Kelvin blackbody radiation in the presence of a 300 Kelvin Earth that the satellite is orbiting, a 6,000 Kelvin star shining light on us all the time, Moon and Jupiter flying through the beams, a magnetic field that the spacecraft is flying through that influences the response to the radiometer. All these factors have to be taken out of the data in a time series and then maps reconstructed. So these maps were generated by subtracting the data from the A and B radiometers at each channel. These maps from adding them. This signal down the middle is due to the galaxy. The main result of that paper is this autocorrelation function of the fluctuations in the temperature on the sky as a function of angular separation. And the dashed line here is the prediction of, at the time, I think it was a cold dark matter, cosmology, inflation stuff. This is the detection that the paper had. This exact same analysis pipeline was applied to the difference maps, and that's where the data came out there. This is why people believe that paper. I mean, people worked really hard on the data reduction, but all those systematic effects I described have lots of opportunities to come in and corrupt the data in ways that are difficult to anticipate. When you have the opportunity to create a quadrature signal, something that is sterile of signal, but has many of the same noise properties and subject to the same systematics, it just is a really good way to help convince your audience that your results are right. So, and that's, I think, yeah, that's it. So. Okay. Yes?
Taking frequencies.
Yeah.
In the double demodulation phase, you got 7 at 1.3 and 5.7 for those two.
Let me zip back.
Something like
Yeah.
that. How do you pick your frequency?
So, the inputs to that are, it's sort of an art, but it's not very complicated. 1/f noise, you want to avoid that. So as fast as you can go up to where capacitive effects or phase shifts will be a problem. So if you're doing a low temperature experiment, your signals are probably going through pi filters on the way into a cold stage. Those pi filters all have some frequency response. They're meant to filter out RF, but they'll have some effect even at 10 kilohertz. You want to stay far from that because those aren't meant to be stable, precise components. They're meant to filter broadband noise. So you want to figure out where the happy area is between where 1/f will become a problem, and on the other hand, where capacitive effects or other AC effects will spoil your measurement. You may be pushed towards the lower frequency end of that. You may have to start riding up a little bit on the 1/f noise because you have really massive filters. There's some question about whether you want to be at incommensurate frequencies to the line frequency, like 13.1 hertz, or if you want to be at a multiple, or submultiple, I should say, of the line frequency, so that the effects of 60 hertz are stationary in your measurement, in your data. So you could also run experiments at 15 hertz, or 30 hertz, or 10 hertz, where the effect of line power will be a DC offset in your measurement, but it may not wander. So there's sort of two schools of thought to that. Usually, being incommensurate and minimizing the amount of pickup is better than hiding it into your DC, but there are times when you could do either one.